Today I'm going to be talking about not transitioning from SQL to NoSQL, but choosing the right tool for the right job. There's a lot of instances where we try to fit something into a SQL database that should not go into a SQL database. And there's sometimes when we try to do the same with NoSQL. So the idea here is to get a good bearing on how to choose what data goes where. And if the data happens to be in a NoSQL database, how do you mimic what we do with SQL? So I work for Redis. Redis is a NoSQL database, key value database. Remember, it's key value, no value key. If you say it that way, it sounds weird and people might think you're crazy. So I am a senior applied AI engineer. I've been doing the whole AI thing for about 6 years. Before that, I was doing it as a hobby, and then I got serious about it in around 2015, and I haven't looked back. I'm a Java developer. I've been doing Java for since 1997, so however many years that is. And I'm a Java champion. Yay! And you can find me at Bodden on Twitter. And my GitHub account, it's full of goodies that you can go in there and steal at your leisure. All right, so let's talk about SQL versus NoSQL. And again, it's all about choosing the right tool for the right job. We're going to get into why would you pick a NoSQL database versus SQL? And we've seen the evolution of NoSQL starting in around 2008 or so. Databases like Cassandra, key value databases like Redis, MongoDB, document databases, BigQuery, big data, all that changed basically how we deal with data. And the reason was that we basically started getting way more data that we used to have before, and most of that data started becoming unstructured data. Very typical to have free-form documents, free-form JSON, and it was very hard to try to disassemble that data, put it into rows and columns in a relational database, and then try to get it back out in a way that was usable. So in SQL versus NoSQL, we have, again, the rise of the SQL databases since, time immemorial. And it was a time where we had domains that were well understood. Banking, insurance. If you look at a schema from one insurance company to the other one, you will see patterns that repeat themselves over and over and over. Same thing with banking and financial services at that time. As you start getting all kinds of different data, including customer-generated data, then those fixed schemas no longer can play the role that the applications require them to play. So with Web 2.0, social media, user-generated content, the NoSQL movement started basically with a lot of different types of databases in caches. Redis started as a cache, and evolve into a database. Then we have, we're going actually back around too. NoSQL databases scaled, provide the scale that SQL databases couldn't. You have to do sharding with SQL databases, relational databases, to be able to scale. And it was a difficult, error-prone approach. Now, SQL databases are going back around and taking some of the lessons learned from NoSQL databases and implementing some of this scalability, architectural changes to them. So we have a world now that it's a combination of a lot of different databases. You also have multi-model databases where the data types could be a graph, it could be a document, it could be vectors, it could be a vector database. So we have a lot of different modalities for databases. And again, the goal of this talk is for you to pick the right ones. So the relational versus NoSQL mindset, it's one of the things that I want to transmit to you. And when you deal with relational databases, you're thinking about the data first. The data is king. The data needs to survive changes to the company, application after application. The schema was king. It was not to be touched. And if you needed to change it, it required a lengthy arduous change process, including sending memos and letters. Dear DBA, I would like to have one column with a Boolean. Here is my firstborn child for you to add that column to the database. And it was difficult times. I remember working at an insurance company and having to beg for it's like, we keep on doing the same thing with these two columns. Can we just have a column that have the thing that we always do? And the answer was typically no. So I think that's how kind of we got into Y2K. Remember Y2K? You guys are too young, but so in the world of relational databases, we take data as the thing that it's fixed in time, the thing that it's not to be changed. We created schemas out of that, and then it's up to the developers to figure out how in the heavens to work with that data, which might include, if you've seen a SQL query with more than 10 lines, you know what I'm talking about. You basically look at it and you're like, I wrote this SQL query 2 hours ago. I'm looking at it again. I don't know what it does. So that is one of the problems that you have when you have a data model that it's highly normalized to survive any applications, and it's future proof. And we all know how good humans are predicting the future. So we make all these guesses about the schema, and it's set in place. It's 1995, and we're thinking, this will last us until the late 2010s. And guess what? It doesn't. Application requirements change drastically. The data that we were getting changed drastically. The amount of data was the one thing that overwhelmed relational databases in the early 2000s. So the application became the last thing to think about. So if you remember time frames to build applications in the 90s, where how long will this project last? It's like probably 5 years. Can you imagine building software right now that somebody tells you, well, we're going to build this in 5 years. That's our window of time. It's like, whew. Now it's like, well, we need to build it in 3 months. We'll see if it works. And if it doesn't, we'll kill it. So the way that we build applications, the way that we think about data has changed drastically. So in the NoSQL world, now we know that we need to live in the moment. We need to take our application requirements and find out how we can make that data better fit the thing that we're trying to do, the thing that might actually make money for our companies. So the equation is reverse. You start with the application in mind, or it could be multiple applications. You still will have to do a compromise in terms of designing the data, but it's not that the data goes first and it's always columns and rows and tables. It's could be in a format very different from what we used to in the relational world. It could be a JSON document. It could be a graph database. It could be a bunch of vectors coming out of a machine learning model. So the type of data and the models of data that we have nowadays are very rich. Therefore, allow us to pick the best model for the application that we're trying to build. So it goes application, data, and then schema. So the application dictates what needs to happen with the data or how it needs to be shaped. All right, so the lesson here, and you've probably heard this saying many times, naming NoSQL was a little aggressive. He's like, we'll never use a relational database again. And I think it was a marketing ploy, obviously. So the reality is that it's not only with SQL. SQL just happens to be one of those data formats, data modes, that it's very useful in specific cases. But in some other cases, it gets in the way of developing great applications. So I work for Redis. And I'm going to give you a little intro to Redis. How many of you have used Redis before? Let me see a show of hands. All right, nice. So Redis is what we call an in-memory first key value database. And I say in-memory first because we optimize for memory, but your data can be persisted to disk too. We just happen to play better in that field first because it's closer to the battle lines, to the battlefront. Where's your application dealing with the data? In memory. Disk, it's, in my mind, an afterthought. And the way that things are changing in the world, the lines between memory and disk storage are getting blurred. They're disappearing. We started with flash memory. It's like, well, it's kind of like a disk, but kind of like memory. And slowly, we're going to get to the point that we're going to stop saying memory and disk, and we're just going to say storage, because it's going to be too hard to classify how it was implemented. So Redis stands for Remote Dictionary Server. Now you know. So, like I said, memory, in memory first, it's our approach. We optimize everything for the modern memory architectures, GPUs, CPUs, multi-core. That's the idea of being in memory first. How to work better in that environment and provide the highest throughput possible. We don't have all the bells and whistles of a lot of different databases, but typically we defeat them in performance. So Redis is optionally persistent. You can decide what things get persisted, so you can use it purely as a cache, where the data is volatile. If that node disappears, then that data is gone. Or you can basically have it persist to disk, which happens very similar to a lot of the journaling NoSQL databases, where every command or every delta that goes to the database goes into a log, and that log gets compacted into a binary blob. And if the node goes down, when it comes back up, you bring the binary blob to recreate the memory, and then you replay the log on top of that to get to the final state that was saved. All right, so in Redis, everything is a key. It's a key value database. Everything, it's a key. But the value could be a lot of different things. For most of you that have used Redis as a cache, the value, it's a string. You take maybe a full-blown HTML page and just throw it in there, and when that request comes back, it's like, here's your page. So it's a very simple format. All you can do is put it into the cache, ask the cache whether it's there, and retrieve it back out by that key. So you need to know the key to be able to get the value back out. One of the cool things about Redis that made it very successful as a cache is that you can have a time to live for any key. So as you insert a key into the database, you will say, oh, well, this needs to live for 5 seconds. And then after those 5 seconds, it disappears. So you can do a lot of things like least recently used, or evict the things that haven't been used in a long time. And that's why Redis succeeded very well as a cache. But there's other data types. There's, for example, you can store bitmaps in Redis and have operations to work on those bitmaps. And that's the magic of Redis that most people haven't really discovered yet. It's that for every type of value that we can store, there is a whole set of commands that implement a lot of those algorithms that we learn in uni that basically do specific things with that data type. So for example, if it's a hash, there's a hash map or a dictionary, there's ways to basically operate efficiently on that dictionary. And we provide that interface as a set of commands that operate on hashes, for example. So there's a set of commands that operate on strings, on bitmaps, on bit fields, hashes. Hashes is kind of one of the workhorses of Redis because it matches well with a DTO or a data object. So when you have a flat data object that requires persistence in memory and to be used in an application, hashes are a workhorse. Really good key value pair, key value pairs, key value pairs. Inside, so that whole hash, it's pointed to by a key. So it's you can think of a map of maps. We also have lists, sets, sorted sets. So for example, if you've seen leaderboards, where let's say you have an online game and you basically want to rapidly be able to calculate who is the highest score in a distributed system of a million users. A lot of gaming companies use us to basically do leaderboards because of how efficient it is. So sorted sets are very good for that. You basically have a set, but each value also, each element in the sorted set has a numeric value associated with it that you can use to sort it. We also have geospatial indexes. hyperlog, which is a probabilistic data structure. So there's a lot of things that Redis does in terms of asking questions of big data that can be replied to in constant time, regardless of how big the data structure or the collection of data became. So for example, if you have a system where you're trying to figure out during a sign-in page whether the email has been taken already. So you can use, for example, a Bloom filter to ask Redis, have I seen this email before, and get a sub-millisecond answer instead of having to go to your user's database and say, select star from where user email equals blah, and then wait for that round trip to say, sorry, that email has been taken. So with things like probabilistic data structures in a remote dictionary like Redis, you can avoid a lot of that stuff that is computationally intensive and costly when you're running your application. We also have streams. Just like Kafka, it's a stream-based system. We have a kind of fast but smaller version of that. So Redis streams allow you to basically deal with very high volume of data, but obviously it doesn't have all the bells and whistles that something like Kafka would have. But the idea here is that it's used for like sensor data. So a lot of places that do, for example, readings of temperature, barometric pressure, things like that, they use Redis because they can send a lot of data to Redis and make it actionable. So you can do things with that data in memory. We also have a time series data structure, and the one that we're going to focus on today, which is a JSON data structure. So just like databases like MongoDB, it's a document database. Redis, it's a multimodal database, depending on what data structure you use. So in today, we're going to be playing with JSON, which makes Redis a document database too. So I'm going to give you a short tour of Redis for those of you that haven't played with it before. And I have a little cheat sheet here, which I'm going to put to the side. So this UI that I have here, this is Redis Insight, which is a GUI to basically interact with Redis. And I have Redis running in Docker, along with MySQL, since we're doing a MySQL Redis translation type of example. And in here, I'm going to connect to that database. And you can see that I have a set of collection of elements. So Redis can organize all the keys that you have. Redis Insight can organize those keys for visualizing them. But again, the beauty of a key value system is that each key, it's independent of anything else. It might follow patterns that allow you to group them with other keys, but they're really just their own little island. So in here, I have a bunch of JSON documents stored in the database. If I click one of those, you can see that there's a value to each one of them. If I click on this tree view, then Redis will use the key pattern, so the prefix of the keys, to basically aggregate them into collections. So for example, you can kind of start guessing that the application I'm going to be playing with, it's about movies and actors and DVDs and rentals. You can see here that I have an actor collection. If I expand that, you'll see that each one of those, the data type is JSON. And if I click one of those, you can see that here is the name of the actor. These are all fake generated data. So the Penelope Guinness, I don't believe exists. So now let me open the CLI. So in Redis Insight, we have something called the CLI, which is the command line interface. Now I'm going to make it a little bigger here for everybody's eyes benefit. So with Redis, you can interact with it from the command line if you want to, or from a UI like Redis Insight. But in here, what I'm doing is setting some value, setting some key to a value. So the key, it's called some colon key, and the value, it's 1, 2, 3, 4. So if I put that in the database, Redis just replies with very simple responses, okay, or some kind of error if something went wrong, which typically doesn't happen. So now if I go back to my browser and I refresh the data, somewhere in here, I should have a, let me see, let's filter. So this would be a string. And there's my key that I just created. And notice that it creates kind of like a namespace for it. The convention in Redis is to use the colon to basically separate segments of the key, and that way you can create collections. So you can have something, application name, colon, class type, colon maybe, subclass type, and that way you can organize your data, but it's not rigid like a SQL schema. Allows you to basically be very flexible in how you design the system. So if I click on this key that we created, you can see that the value is 1, 2, 3, 4, which is what we sent here. And of course, you can also do that from the CLI. So I'm going to show you a couple more examples in here. So this is the one that basically makes Redis great as a cache. So I'm setting another one, another key. Naming is one of the hardest things. So when you're creating your demos, my imagination just dies immediately when it comes to naming things. So we have here another greatly named key called another one with the value 8675309. If you're old enough, you know what that number means. And then has an EX10, which means I'm going to expire that key in 10 seconds. So if I add that, and I'm fast enough to type get another, oh, see, I'm too slow. Get another one, I have it there. But if I keep on doing that, at some point, that key disappears. So that's one of the reasons that Redis became such a powerful cache, because it's had expiration of the data built in. But if you were to touch that data or edit it, it would say, oh, okay, we have to reset the timer now. And that it is what makes Redis a great cache. So and a lot of you have seen this type of functionality. Now let me show you some of the things that you might not have seen. And I'm actually going to jump straight to the JSON to do that. So in here, I'm not going to type all this, but I have a command here that basically creates a JSON key. And it's JSON.set. And the key name, it's bicycle:0. Now, if you know JSON, you probably know JSON path, which is a way to basically describe a specific position or element of the JSON. In this case, I'm saying I want to store this at the root element of my JSON. That dot right there means the root element. And then I have a full-blown JSON document attached to this command. So once I run that, obviously I can do a JSON.get and do, let's copy and paste, make it faster. So I can do a JSON get bicycle:0, but I can also go back to my browser. Let's switch back here to filter just to see JSON. And now I have a bicycle collection because I did bicycle:something. And you can see now that I have my JSON document, and you can inspect it here in this nicer view than just a command line view. All right. Now, one of the other things that I want to show you before we go back to the slides, it's the commands in Redis allow you to do very specific things that are potentially fine-grained against your data. So if you're building, for example, a web service, and you have a massive JSON document, let's say that it's, half a gig of JSON, which it's actually not unheard of, but you only need 2 values of it. You need like a subtree of that document. In most systems, or if you were to use Redis just as a string data type, you would have to retrieve all that JSON. Then on your client, you would have to parse the JSON and figure out how to get to that value, extract it, compose a response, and send that to your users. It's actually very expensive. So in Redis, instead, you can get to specific elements of the JSON and only return what you need. So in this case, I'm returning everything. But I can also do something like this. So these are JSON documents that specify a bicycle. In this case, now I'm going to get only the model of the bicycle by using a JSON path notation. So I can say $.model, and I only get the brand, which is Jigger. And you can see that that model is here on the full-blown JSON document. So perfect, that's great. You can basically do fine-grained manipulations of JSON. But what if you want to do something more complex? And if you have something more complex, we can, Redis has a built-in search engine. And the premise of this talk, actually, I'm jumping ahead of one of my slides. It's that NoSQL plus a search engine kind of equals the SQL capabilities that you're used to, with a little bit of data engineering and manipulation. So I'm going to show you how the Redis search engine works by creating an index on that bicycle collection that I just had in there. So in here, I just created an index. And notice that in Redis, all commands have a prefix. So all the JSON commands are JSON.something. The FT commands are the search engine commands, which stands for full text. So it's a full text search engine, but it's also a vector search engine now. It does a lot of different things. We added bells and whistles to it because it was needed. But the FT create command creates a index, a search index on all the JSON documents that have the prefix bicycle. And notice that I can actually select specific type of search index schema fields to treat the different values in the JSON differently. So I can treat something as a tag value, which means that if I have the specific string, I can find that value by its value. I can find that element by its value, or I can index it as a number and say, I want all the JSON documents where that value is within the range of this two numeric begin and end. I can also index something as a full text element, which basically allows you to do partial keyword searches, soundex algorithm type of searches. So all the things that you're used to in a full-blown search engine like, let's say, Elastic. All right, so once we have that index created, I can do things like a select star from the database, which is typically not a good idea with NoSQL because NoSQL typically is associated with big data. So this is a dangerous command to do, but we're doing a demo with basically Mickey Mouse data, so it's not that dangerous here. But you can see here that if I do an FT search command, so we had an FT create to create the index, FT search to find on the index bicycle everything. And again, the ability of this is that this is data that you have in memory. So imagine that you have an e-commerce system and you have sessions happening during a massive sale and you have created promotions, like some kind of coupon or something like that. You could basically search through your in-memory sessions and find out who has put that item in their cart but hasn't checked out yet. So you could do very rapid decision making and say, all right, let's send them a better coupon to make sure that that item that they put in the cart doesn't get abandoned. So, and that's kind of like the business intelligence, real-time data approach that Redis is used for. All right, so let me show you one more search command here. And the prior command was a very broad command. This one, I'm doing an FT search, and I'm finding again against the bicycles, but I'm telling it I want only bicycles where the model matches that keyword. And of course, I only have one element in the database right now, so that's the only one that we can get. But if I were to change that value to something else, you can see that it returns nothing. So just like a SQL query in a relational database, you can now query your JSON data very rapidly and be able to react to it. Okay, so now let me switch back to the slides. All right, so that was our short tour of Redis. So again, I show you the JSON documents in the search engine, and that's going to be the concentration of this talk. That the combination JSON to me in Redis, and if you use Mongo, you probably understand why. It's the most flexible data type that we have. And it allows you to mimic a lot of the patterns that we used to try to recreate with relational databases. But we have the data in the tree structure that it was meant to be in. All the hierarchies are already built into the document, rather than having to use foreign keys to build a tree of data artificially. So This is a Spring talk, by the way. So I'm a Java developer. It's my language of preference. And at Redis, we created a framework to basically be able to do all of these things through Spring in Java. And it's called Redis Spring. And some idiot at the company created it. It's like nobody told him not to do it, and then he just did it. And he hasn't been fired yet, but it's probably going to happen soon. I'm the idiot. Yeah. All right, so Redis extends Spring Data Redis. So anybody has used Spring Data Redis? Show of hands. All right. So it's Spring Data Redis is a Spring Data framework that allows you to interact with some of the basic structures that we have in Redis. And Redis Spring extends that to add all the new data structures that we have and also the search engine capability. So you can have much more powerful queries and things like that. So in Spring Data Redis or Redis Spring, we have repositories. So if you work with Redis or with Spring, you are used to Spring Data repositories where you can declare a method that says, find this by this and this, put 2 parameters in the method and not implement it. The framework itself looks at the method signature and generates at runtime the access, the data access to retrieve that data. So we have proxies that basically look at the method signature, figure out how to build one of those FT search commands, and then hit the database with that. So we have 2 types of repositories. Today we're going to be using the Redis document repository that basically works with JSON. And then there's a Redis enhanced repository, which works with hashes. In Spring Data Redis, they have already a repository that works with hashes. So all I did was extend the functionality of that one. So what do we get out of the search engine? We get a full text search engine. We get the ability to build secondary indexes over Redis. You can index anything that is in a JSON or hash data structure. You can index. You can do incremental indexing without performance loss. So the indexing is very fast. Obviously, it's all in memory, and it's meant for an in-memory environment. It provides the querying that you saw here, but also aggregations. So if you work with systems, NoSQL systems like MongoDB or a lot of the different NoSQL databases, they typically have some kind of aggregation pipeline API, which allows you to basically take a piece of collection of data and then apply transformations to turn them into some value at the end of the day. It could be basically calculating, what employee it's the one that's basically taking the most sick days in the company. That's probably me too, but the search engine also allows you to do autocomplete, for example. So if you have data in memory and you want to create one of those UIs where you autocomplete what the user is doing, you don't have to go back all the way back to the relational database to do that. Redis will index specific collections to be optimized for autocomplete. So the typical use cases that you find in web applications, we cover to make life easier. So here is what a document looks like in Java now. This Java class here has an ID, which comes from Spring. And you can see that it has a bunch of fields, and it's annotated with the document annotation. And inside of the parentheses, it says Sakila film. That is the prefix that the keys for those documents would have. So every time you try to persist one of these Java objects, it's going to go into Redis using that JSON set command that we saw. And the key is going to be sakila.film : and then the ID value of that. So it's a very, very traditional Spring application. It's hard to actually know that you're not using a relational database because it just feels the same way. It's just a little faster. And of course, on the right-hand side, you have the equivalent JSON that one of these objects will generate. So Redis document repositories. So this is what I meant by you declare the methods to use to access the data, but you don't have to implement them. And these are some of the basic ones. For example, you can say, this is a collection of films. So you can say that I want all the films passing just a free-form text. What that means in Redis Spring is that any field in that object that it's indexed with the full text search, we're going to search over all of them for all the objects very fast. So this is a free-form search that would say if that query, it's in the title or the description or any other text field in that object that was indexed as text, then we're going to find it. The second one, you can basically provide the properties that you want to target. So if I say search by title, and then I pass a parameter title, it's going to find, if you remember that FT search command that had the @%, the name of the field, and the value, that's what we're doing under the covers. And also you can do more complex searches where you string things together, like search by title and length, less than equal some value. So you can pass the title and the length, which is an integer, and Redis will basically, Redis Home Spring will build the right query for you. So here's an example of what happens. So the top search method gets turned into this FT search command. The second one gets turned into something a little more complex. And notice in here that inside of those commands, you have a sub-language to be able to do different things. So in here, I can say, find any movie where the title is Crow, Grease, or Cowboy Doom. Again, this is artificially generated data, so most of the time it doesn't make any sense. The last one, notice that it searched based on two fields, the title and the length of the movie. So I can say, find anything with the title that includes anywhere in the text. So this is like includes or in the word speed, and the length is between 0 and 120 minutes. So a lot of flexibility to build your data access layer. All right, so let me show you now. Let's switch to IntelliJ. And I have the application already running. So just to show you that I'm not lying, the application that's running, it's talking to Redis that's also running. And I also have my SQL running. So let me show you that repository first. So here's some of the domain objects. So let's look at the film domain object. And this one now has more annotations than prior. So notice that we have, again, the document annotation. We have the ID, but we also have the annotation searchable and index, and also reference. So the reference annotation allows you to connect one collection to another one via the key value reference. And the index allows you to index a lot of different data types as numeric, or tags, or geo. But there's a special one, searchable, allows you to index a string field or a character field as a full text value. So those are the ones that allow you to do free-form searches and find whatever you need. So once you have one of those, typically you create a repository, as we've seen before. Here's the one from the slides. And then I can use those in this case, a controller. So for more complex applications, typically the pattern is to have a service of some sort that uses multiple repositories to aggregate data from different places and then create responses for the service. But since this is a demo, I'm going straight from the controller to the data access and returning something to the user. So the first one that I care to show you is this big enough? I'll make it a little bigger. Yeah. So in here, we have a get mapping to films. And notice that I'm doing the repository. The repository here is that film repository. And I'm doing a find all. And that is one of the built-in methods that you don't even have to declare. Those are part of the interface available to you for free. Then the second one, it's doing a films, passing a query. And you can see that there's a path variable query, and then we'll pass that to the search method in the repository. Search is a special method in Redis Home Spring that allows you to do that free-form text search. And then finally here at the bottom, we have two methods called by title. So one just takes the title and does a search by title, which is part of our repository. And the other one does the search by title and length less than equal to those two values. So now I have a little HTML page where I added those links already to test this. So the first one, when I click on that localhost 8080 films, is going to create that FT search method, but through the Java interface as we've seen. So in here, you can see that I get my JSON, and it's incredibly fast, but also what you would expect from a database. If we do finding all the films related to Japan, you can see here that I have a collection of films that are related to Japan. So you can see, for example, I have in ancient Japan, let's see. And again, remember, this is artificial data, so there was a collection of sentences that were randomly glued together to create the data. But you can see the power of this. It's extremely fast. It's in memory. It has the flexibility that you would need from SQL. And allows you to really, really do incredible things. So I'm going to jump back to the slides now and show you one last thing before we go. And so the database that we're dealing with, it's called Sakila, and this is the flagship database that MySQL distributes as a good example of a normalized relational database. So what I did, I thought it was a good challenge to take this relational database and try to work with it in a NoSQL environment. And again, the premise of the talk was that NoSQL plus search kind of gets you to do SQL. And for this specific problem, I used the aggregation pipeline that Redis, the Redis search engine provides. So now let me show you the part that is the star of the show here. Yes, here we go. So there's a store function in the Sakila database to rent a DVD. And it kind of goes like this. It's the DVD in stock, create a rental record, calculate the customer balance, take the payment. And we're only going to tackle number one. It's the DVD in stock. So the store function kind of looks like this. You call select inventory in stock, and you get a value out. The value is 1 or 0. It is in stock or is not available. Now, this is the implementation of that. If you work with store procedures and store functions in Oracle or MySQL, you know that they are not a fun animal to deal with. You were supposed to laugh harder at that. I'm disappointed in you. But to do this in Redis, we basically have to answer two questions. There are no rows in the rental table. That means that the DVD is not out. Or any rows in the rental table have the return date set to them. And to do this, I have to denormalize the database a little bit. So I took the film ID that's in the inventory, and I recreated it in the rental table. I did the same with the rental duration and the rental rate. So you will have to do compromises. Typically, they include denormalization, data duplication to basically mold a SQL, original SQL schema into a NoSQL schema. But you gain a lot of other benefits. So this is the rental object. That's the data duplication. And now just let me show you, I'm going to scroll to the end. I obviously didn't do really well on the time management aspects today. All right, so that's the original store function. And this is that in Java using Redis on Spring. And you can see if you use the Java Streams API, you know that it's so nice to be able to daisy chain methods and transform data and collect values. And that's what we're doing in here, but it's actually creating FT search and FT aggregate methods that hit Redis to get that data. So you can see here that I'm filtering by inventory based on the inventory ID. I'm doing a group by and reducing and counting those elements as the variable rented. And then I'm basically calculating the items that have not been returned, so I can answer those two questions to determine whether an item is in stock or not. And at the bottom of the screen, I have a Boolean calculation to do that. So much easier than writing a MySQL store procedure. And now if we go back to the UI, you can see that I have here a demo for whether that inventory is in stock or not. And for this element, yes, it is. You can see how fast that is. And for this other one, it's not in stock. So again, the premise of the talk is that you can take SQL and a search engine and a NoSQL and a search engine and get close to what you are normally doing with SQL. So the two scenarios are that you either have an old database that you need to port to a NoSQL system, or you have just a portion of that database that needs to be faster and more distributable. So this is how you basically think about moving that data from one place to the other. And also determining which is a system of record. Maybe the relational database becomes a system of record, and the NoSQL, it's a view of that system. So you would have to have some kind of process that basically shuffles data from the relational to the NoSQL. Or vice versa, you might have a system where the data, it's documents. So the system of record would be something like Redis or MongoDB, and then you shuffle that to a relational database for analytics maybe. So keep in mind that you don't have to use one world or the other exclusively. They both complement each other. Okay, one more slide and I'll let you guys go. So again, Redis can accommodate complex data models. And with this powerful search engine that has this aggregation capability, you can do a lot of things that actually are harder to do in SQL sometimes. And you get the added performance. The repository for this demo, it's on my GitHub account. And thank you so much.